I guess I really kind of wanted to say a few remarks before I jumped in. The first is I really, really wish I could be there in person. This is stuff that's near and dear to me. I've been interested in a really long time, and it was a very painful decision to realize just logistically there was no way I could swing traveling to Aberdeen this week. So I'm super happy I get a chance to contribute a little bit, and I enjoyed it. I've actually been on for about an hour or so, listening to Jim's talk and the conversation. It sounds really, really interesting. So so that said, I also kind of struggled to figure out what would be the best thing to present, sort of looking at the expertise that's already in the room. I was trying to figure out, well, what can I add that people here don't already know. So what I think I might be able to do is sort of link some of the basic, really core organismal physiological principles to growth modeling, to think about how we can actually generate sort of expectations for the types of changes we expect to see in growth. So what I'm going to do is actually go like really, really back to basics with the idea of sort of building a foundation and link those to a lot of the growth models that we use. The other caveat I was going to say is I unfortunately busted my arm a couple weeks ago, so I had grander ambitions for what I wanted to do in this presentation. So I ended up keeping this on the brief side with the idea of basically maybe springing conversations sort of similar to what you guys had after Jim Thorson's talk. So it's by no means going to take the full slot of time, but I assume that's probably in the best interest, particularly since you guys are at the end of your day. What else did I want to say at the beginning? Yeah, and I guess this is sort of the informal, so if people want to chime in, if there's an easier way for people to do that, like I'm just staring at my computer, so if people just want to shout for me to stop or shut up or whatever, yeah, go ahead and do that. Okay, so the basic thing I'm going to try to do is sort of think about growth from a bioenergetics framework and link that to the growth models and size and age models we use a lot. And maybe this is obvious to everybody, but the thing that I find both fascinating and frustrating about being interested in growth is, growth is a lot like mortality. It's a process that happens, and we can't see it directly, but we see the consequences of it. So we're always trying to kind of make inferences by looking at changes in the states that we're interested in, whether it's a size of organisms or population abundance, and inferring what those underlying processes are. And I think that's the core challenge we face when dealing with estimating these things. And I also think it's core to sort of understanding why it's challenging to make robust predictions and even robust hindcasts in terms of what is the contribution of, say, temperature changes, oxygen changes on growth. And it's precisely because lots of things are affecting the state variables, and one of them is the growth. And I suspect that Christine and Melissa, they'll probably talk about some of the stuff that we've done to try to do the best we can to kind of even just track growth changes based on data we have. That turns out to be challenging. I'm going to leave all of that and just get to the underlying sort of bioenergetic basis. And I thought it would be useful to kind of talk about where I come from here. So I sort of have a foundation in actually, it was a lot of freshwater ecology, but I learned from mentors when I was both an undergraduate and graduate student in both master's and PhD, starting with Paul Webb over on the left. Paul Webb is mostly known as an expert in fish locomotion, but he's the first person who kind of taught me about thinking about organisms as a system. That was like a revelation to me, and particularly as a system that basically processes energy, and that was sort of a big eye-opening thing. I then moved on to work with Peter Sorensen, and he's mostly known as an olfactory physiologist. But what I really got out of Peter, which I think is really relevant to the discussion that you guys are having, is being really critical about generalizations and being really a stickler for thinking about the core physiological processes that are going on. So it really taught me to be kind of critical for, I think it really taught me if something sounds too good to be true, it probably isn't. And then lastly, I was really fortunate to do my dissertation work with Jim Kitchell. He was like the complete counterpoint to Peter, which is the being able to be synthetic and draw connections to ideas and to connect ideas across scales. And that's what Jim was so fantastic at doing throughout his career. So he not only took the principles of bioenergetics, but then saw how you could apply that to think about populations, thinking about food webs, thinking about ecosystems. So the stuff that I'm going to present is kind of an amalgamation of all that stuff, and then layering on stuff that I've done subsequently with people like Carl Walters and Mark Mangel, in terms of thinking, well, how does that affect sort of population models and growth rate models? So the basic idea, this is basically copied from, so if Jim Kitchell were to give a lecture on bioenergetics in his fish ecology class, there would be a graph that looks kind of like this, which is sort of the basic idea of how bioenergetics people sort of think about organisms as an energy processing machine. And the basic idea is that an organism consumes a certain amount of energy and then has various energy allocation issues, some of which it has no choice on, and some of which it does have some choice on. And when Jim would always present this, he would always sort of make the distinction between what he called taxes and rent. So taxes are always proportional to your revenue or income, while rent is sort of fixed costs that you have to pay. So in a bioenergetics framework, I don't know if you guys can see my pointer, energy gets come in and various taxes sort of get taken off of that, and the taxes are basically, you can't absorb everything. So there's assimilation losses and to people losses, and then of that you can't absorb all of it, so there's nitrogenous waste losses. And then finally, when you simulate that energy, there's actually cost to actually simulating energy, so there's energy due to digestion. So going from the energy consumed to energy that you actually can use, there are all these different taxes that get taken up. Oops. And those are, of course, the organism has no choice on those just happen. Once you get to this bolus of energy that can be metabolized, then the organism has basically a rent it has to pay. It has to keep itself alive. And that's sort of the standard respiration or the standard metabolic rate. So that's all of the energy that goes into maintaining all of the things that it needs to do to keep the cells and the organisms alive. And then finally, you get to the bottom piece there, and of all that energy is now been processed, that's the energy that the organism can then make choices about how it wants to allocate that energy. And at the broader level, there's basically three sort of choices it can make. It can sort of choose to swim around as fast as it can and burn all the energy into activity. I don't know why it would do that, but it could. It can allocate some of that into tissues, somatic tissues in terms of growth, or it can allocate into gonadal tissues. And those turn out to be pretty complex allocation decisions that we honestly don't understand too much. And it turns out even those growth decisions actually have other allocation issues associated with them, because even if it decides, hey, I want to allocate this to tissues, I'm not going to allocate it to activity, there's lots of different tissues it could build. And the three main ones that we often think about are structural, storage, and gonadal tissue. So gonadal tissue is basically energy allocation into reproduction. But the structural and storage are really different, and they're manifest really differently in terms of the things that we track in terms of growth rate. So structural are tissues like basically bone and nervous tissue. Of course, bone, once you build bone, you typically don't unbuild that bone. So allocation into structural tissues is quasi-permanent, and you're going to basically, you're choosing to sort of maintain that from sort of now on. And then, of course, we know that because generally we don't think of fish shrinking in terms of their length very much. They typically maintain their length, but if they do shrink, they're shrinking in terms of other things. The other decision, of course, is they can allocate what we call storage tissues. The storage tissues are fat and muscle. Obviously, muscle does more than just store things. It actually helps the things move around. But that's manifest primarily as weight. And that's the thing that can, obviously, you can increase in weight and you can decrease in weight depending on the environment conditions. And then obviously any energy allocation to gonad, if you depends on when you happen to be weighing the fish, that could obviously be detected as a change in weight, but those gonad tissues are going to be released and then it's going to be lost. But the sort of the key point behind all of this is really just to understand that growth is looking at changes in tissue. That process itself comes from a variety of allocation rules that the organism is using to figure out where to place that energy that it's consumed. And those allocation rules are really not understood well at all. Carl Walters and I did kind of a fun little paper, and we went into it thinking we could try to come up with sort of some first principles, using just basic optimization rules of how should it choose to allocate between structural and storage. And everything that we came up with, and then we ended up sort of simulating what would be a fish exposing to a variable environment, came up with complete nonsense types of behaviors that we didn't really believe. So it was just really hard to come up with what, first principles, when should it allocate to structural tissues and storage. Yet, just like a common sense basis, we really know that they exist in some way. So here's a picture that I stole from Christine, who then I think stole from DFO. This is just, 2 cod, 1 plump, 1 skinny. And, I think we have an intuition that if you fed a bunch of food to this skinny cod, it's probably not going to use that energy to make itself longer. It's probably going to try to make itself plumper because it's kind of in a weird shape. But if you give food to this plump cod, there's a good chance a lot of that's going to go into structural tissue. So we have a good idea that if your condition factor is kind of skewed one way or another, you'll probably try to compensate one way or another. But how that actually happens is we don't really know. And I wanted to flag that largely because most of the data we tend to get on body size tends to be length. Simply because length is just way easier to measure out in the field. I mean, if you're on a boat, it's moving up and down. You can measure the length, that's pretty easy, but measuring weight is going to take a bit of time. It's hard to do quickly. So we tend to get a lot of information on length, but I think we need to remember length is sort of the consequence of this allocation decision. It's probably not going to reflect these sort of shorter term fluctuations that storage would reflect. Instead, it's probably going to reflect more long-term integrated conditions, so not as effective at sort of measuring short-term environmental conditions. So that's sort of the background. Where I wanted to go from here was actually then get into our core growth models and then say, well, how do the main processes that we measure in our growth models, how ultimately do we expect them to be affected by things like changes in temperature and changes in oxygen? And I gotta, just to foreshadow, I'm not gonna have the answer to that, but I'm gonna propose some questions, and then I'll also sort of propose some challenges that I think are really hard, that I don't think that we're not gonna solve those in the short term, but I think we should be doing kind of the easy analysis cognizant of the sort of the limitations we have. All right, so this is my favorite equation of all time. It's the von Bertalanffy growth function. We've all used the von Bertalanffy model in one way or another. We've probably seen a variety of different forms. It takes lots of different shapes. I'm going to start with this very generalized form, and then really use that to highlight the basic principles underneath the growth models, how that relates to the bioenergetic principles I showed, and then mostly to highlight a lot of assumptions that are kind of embedded in it. And then hopefully use that then to link about how we think the sort of growth rate parameters we often use in growth modeling are likely to be affected by environmental change. So the basic idea is we're going to measure changes in body size in terms of weight. We'll get to length in a minute. So right now we're going to be dealing purely with mass. So dW to T is the growth rate. That's the difference between two competing processes. The first is anabolism, so that's the accumulation of energy. That's going to be proportional to biomass, and then the losses of energy due to catabolism. And I will say now that to make life easier, catabolism and reproductive costs can often be bundled together because at longer time frames, at least in terms of what is the resulting body size, they end up basically making our assumptions a lot easier to defend. So our catabolism is also going to reflect some of the gonadal losses. So the idea is that both of these scale with body size, and the body size metric that fundamentally matters is how big the organism is, the mass. And the difference between anabolism and catabolism is the growth rate. So both of these scale with body size at different rates. So here's my anabolism going up with body size and then leveling off, and catabolism in this sort of toy example is just sort of increasing and increasing. The difference between the anabolism and catabolism is the growth rate. So that's the basic von Bertalanffy growth model at its most core and basic. I should mention this anabolism is basically the end result of a lot of that bioenergetic hierarchy that I already talked about. So it's including all of the losses that happen due to absorption and assimilation. That's all being embedded in here. But meanwhile, the other energetic expenses, which would be the standard metabolic rate plus all of the active metabolic rate, that's going to be embedded in this term here. Key things here, the allometric scaling relates to mass, not length, even though length is easier to measure. This H is related to consumption, but consumption, of course, isn't everything because it's all the assimilation. K is related to all of the metabolic terms. Okay, so let's take that the next step. That's not the term we normally see. This is a big, ugly equation, but it's going to build us to a more useful equation. If we assume that energy expenditures are approximately linear with body mass, then calculus works. Namely, you can actually solve this integral to get a prediction of body size at any given age t. So it's purely an assumption that we're making for convenience, because if this term here is anything other than 1, there's no solution that we even have for this. I've done a little bit of work on this to actually say, well, to what extent is that reasonable? We generally think that the energetic losses don't scale linearly. They more scale at sort of a 3/4 power law. But if you add in some of the energetic expenditures for reproduction, n equals 1 is a not terrible assumption, put it that way. So if you do that, you get this long, heinous equation that says, hey, I can tell you the weight at times t. It's a function of that consumption rate term, that metabolism term, and this d, which is the allometric scaling of anabolism to body size. And we can get an asymptotic weight, which depends on, not surprisingly, the ratio of the anabolism to catabolism term, and it's also related to this anabolic or allometric scaling term. So this is still an unfamiliar term. We tend not to use it in this particular framework. This is often called the generalized von Bertalanffy model. But because it's got this weird 1 minus 1 minus d over here, and we've got the 1 minus d over there, and we got the 1 minus d over there, we often make a further assumption. We say, look, what if we assume that the anabolism term scales with body size to the 2/3 power? This, again, is purely a mathematical convenience, and we do that because a lot of things end up becoming a lot simpler in the expression. So there's not actually a strong empirical basis that d equals 2/3. In fact, it seems to be a lot closer to 0.7 or maybe even 0.75. But if you want to make that assumption to get a tidier equation, you can do that, and then you get an expression that actually looks super familiar, where the weight at size t is the asymptotic length. Asymptotic length is, remember, the ratio of the h to k. It's going to now be a function of basically to the q power. And then this whole thing that we see a lot, now this great big k that we're used to seeing in the von Bertalanffy term, that's just our little k that we started with, the catabolism term, times, if we assume it's 2/3, this is going to be just multiplied times 1/3. And this now becomes a nice handy to the cubic power. So this is maybe somewhat familiar. The next step is then actually look at it in terms of length, which is why we don't normally do that. So if we want to do everything in terms of length, we have to make some assumptions of how length and length scale with each other. So we have to make more assumptions to do that. So if we assume that weight is a power function of length, which it certainly is, but we have to assume that the scaling coefficient b is constant, which certainly is not true. I showed you those two pictures of cod. You're going to get really, really different allometric scalings of weight to length. But if we assume that it's roughly 3, which generally on average, if you look over a ton of fish species, it's approximately 3. And then additionally assume that the allometric scaling consumption is 2/3, which again is definitely not true. You can express the growth rate of length in terms of this expression, yada, yada, yada. You do some integration, and then you get the form that all of us have probably seen before, our good friend, the von Bernoulli equation, where length of some t is equal to asymptotic length times 1 minus e to the minus k times h. Here, the asymptotic length is a product of the anabolism term, how basically weight scales with length, and then our k, which is again our metabolic term, which is adjusted a little bit. So the purpose of showing all this is not to have calculus, but really is to show a couple of things. One, this modeling form we use all the time has a ton of assumptions embedded in it. And of course it has assumptions about the underlying model to begin with, but it also actually makes a lot of parametric assumptions. So it makes assumptions that overall energetic costs scale linearly with body size. It makes a big assumption that anabolism scales with body size to the 2/3 power. And it presumes that weight scales with length to the power of 3, and that scaling doesn't change depending how growth is actually happening. So that was actually the one main reason I wanted to talk about that. The second main reason is that these parameters that we measure in our growth models have linkages to bioenergetic processes that we're interested in. Namely, K, that we often call a growth rate parameter, actually is a metabolism parameter. If you go back to the origins of K in our von Bernoulli curve, it really was only governed by the rate of catabolism. So the consumption rate doesn't have any bearing on that whatsoever. The asymptotic size is a combination of all those processes together in ways that are fairly predictable. So I probably should put this up first. So metabolism affects both asymptotic size and the rate parameter. So when changes in metabolism, we anticipate affecting both things like L infinity and K. Food consumption is only going to affect the asymptotic size. So if you think about some of the environmental influences, we're basically getting some clues of what parameters we think will be sensitive and how they're actually going to change. But ultimately, it's the K and H parameters, so K being sort of the mass-specific metabolic rate, and H the mass-specific anabolic rate. Those are kind of the master variables that are embedded within this overall expression. And we have tons of organismal physiological studies that tell us that both of those things are impacted by temperature and oxygen availability. So I think that is a great opportunity for us to thinking about making some generalized predictions about how parameters in these common growth models are likely to be affected by changes in temperature and changes in oxygen availability. So I think what I'm sort of proposing is we have a lot of empirical work, which is great, that perhaps there's also a good opportunity here to start making some baseline theoretical predictions that then we can use the empirical work to sort of directly test. And then one of the last things in terms of making this linkage here, and people in the room can speak about Frey paradigm more than I can. I know Byron can talk about it, and everyone else probably can. Frey paradigm is something that was embedded in me, and I may be wrong, but my sense is in freshwater fish literature, everyone talks about the Frey paradigm, and maybe because he did a lot of work on freshwater fish and some truncates and things like that. But the Frey paradigm was basically a way of sort of thinking about environmental influences and how they affect metabolism. And Fred Frey, one is super smart, way ahead of his time, but he was sort of basically said we can sort of lump things into the ways in which they affect metabolism. And I wanted to put this here because if we're talking about temperature and oxygen availability, they come out as being really different factors. Namely, we think about temperature as a controlling factor because it governs the basic kinematics of metabolic reactions. So temperature is basically a measure of heat. Heat governs the rate at which metabolic reactions happen. That's going to govern both the standard metabolic rate, the cost of keeping the organism alive, and also it's going to affect the active metabolic rate, how much stuff it can actually do. And then the growth rate is probably going to reflect those metabolic rates because it reflects the ability to acquire energy. Oxygen acts in a totally different way, of course. It's a limiting factor, it's a constraint, which means we expect the response to oxygen to be very fundamentally different than it is to temperature. And just one little fun thing that I was just going to just show is the fact that it's not that easy to know a priori whether a particular change in temperature is necessarily going to cause an increase in growth or a change in growth. In retrospect, this is not the best graphic in the world. This is trying to show that same von Bertalanffy growth model with two different sets of curves, one at one temperature and one at a new temperature. If we just look at the solid lines here, this is like our anabolism curve that we started with right here. The blue line is the catabolism curve. Where they intersect, that's the asymptotic weight right here. So that's where we would be kind of in a baseline scenario. Imagine a scenario where there's a temperature change. That temperature change affects the K parameter and the H parameter in different ways. So K is metabolism, H is anabolism. And in this made-up example, the catabolism might adjust by 5%, but the anabolism might increase by 10%. That's going to cause the red line to go up, the blue line to go up. Our new asymptote is where these two lines intersect, and that's going to lead to an increase in the asymptotic size. So I wanted to show this largely to say that this was totally made up, and I easily could have made these differences such that the resulting consequence of a temperature change was a shrinking of the fish. So whether or not temperature causes an increase depends on how K responds to that temperature relative to how the catabolism responds to temperature. And to be honest, that's going to be highly context specific. So we already know, tons of great work like the work that David Condor has done on that organisms are clearly locally adapted to environmental conditions, and what is a great temperature for one subpopulation is not a great temperature for another subpopulation, which introduces a whole other sort of challenge in terms of making these predictions. So this is where I'm going to wrap it up with sort of two thoughts about what might be like easy steps that we might be able to do kind of at a short term. And the first is sort of using the sort of foundational principles of how the von Bertalanffy type of framework of thinking about body size changes and how it relates to underlying physiology and underlying bioenergetic sort of energy allocation questions. Combining that with our information of how we think these basic processes are affected by temperature and affected by oxygen, coming up with heuristics that allow us to have rules of thumb to say these are the contexts where we expect temperature changes to cause particularly large changes in growth, relatively minor changes in growth, and when are they not? And I think it's not going to be, I think it's actually an interesting question because I think the nature of the responses of these rates to temperature and oxygen are really, really different. And I think there's a nice opportunity to basically do a synthesis of the body of work that's done on organismal physiology and link that to these really core, really oversimplified models to build these rules of thumbs. So that seems like a low-hanging fruit that would be super interesting to do. But doing though with the harder steps is that, remember, a lot of our data are changes in length. Length dynamics are just inherently more complicated than weight dynamics because they represent investments in structural tissue that can't be undone generally. We have more of those data, but they're trickier to do. And then similarly, we also don't have a great, and this kind of came up in the earlier discussion about, it's not true that climate change is just changing the overall environment, it's changing the exposure pattern. So it's not like all of a sudden everything is just getting constantly warmer, but organisms are experiencing a new range of temperatures and a new sort of pattern of either daily fluctuation or seasonal fluctuation, and how those variable environmental exposures manifest in length is super duper complicated because of this energy allocation question. So that was what I had. I hope that just prompts some conversation with everybody.
Yeah, that was great.
What's funny?
So could you go back to your proposed easy step?
Oh, sure, yeah.
Let's stop there.
Yeah, I'm trying to, it's about 6 p.m. here. I'm trying to think of anything that's really easy about it.
Yeah, how to get home.
Okay,
How to get, or, do we have the microphone somewhere?
we do somewhere.
Okay. Is the, hi, Tim, it's Tara here. So it's,
Tara.
it's nice to meet you. We've had a long-standing correspondence, but
Yeah.
we have never actually talked, so I was really, really interested in, you come from a physiological tradition. You were taking it back to first principles, growth, and really arguing to do something that I also think is very important, that I approach it from a different route, i.e. not physiology, more of an empirical route, via the von Bertalanffy with all its work. And but I guess it's getting, so I tend to think of temperature impacts on the relationship between K and L infinity in the von Bertalanffy. And that empirically we could get at the amount of variability that temperature induces in that negative relationship, partly because we've got replications. We've got 22 different cod stocks living in 22 different ecosystems, each having cohorts growing over different temperatures. So it's almost getting towards a three-dimensional model where you have temperature incorporated in some way. And so I've been trying to think about that for a long time, and I suspect it's very much along the lines that you're thinking of doing it from a sort of physiological perspective. Would that be correct?
Yeah, I think that's exactly right. I think what you described is exactly kind of what I'm thinking about. It's confusing because L infinity is affected by two processes, while K is affected by one process, but one of those processes affects L infinity. So and we expect both of those processes are affected by temperature, but affected at probably different scaling rates and different functions. So I think what you're sort of describing is sort of like an empirical approach. To basically say, hey, what can we pull out of basically the thermal history of these fishes and their response to try to pull out what that is. And I would basically say, I think we can also combine that with the abundant information we have that's experimentation, et cetera, whether that could be a Bayesian sort of thing where we're using some of the physiological stuff as priors and using that to apply the empirical stuff. It just seems like that would be a nice way to make an initial advance of this hard question.
But I guess I'm thinking at it for a different purpose. I don't want to understand everything. I just want to do one thing, and I want to project growth for different temperature regimes. And ideally, I'd like it to be as generic as possible. So there could be some trait-based component of a model, so that you could then apply it more throughout the fish community rather than tailor it just for one species. And I think William Jung must have had something like this running his projections, his temperature projections for his paper on shrinking fish. He must have been a quick and dirty empirical model, but I don't think it was described in his paper in any detail, but it was probably not too far off those sorts of ideas.
It's not William Chung's. Tim, do you want to talk about the? Do you want to get into the debate about Polly's gill size? Because that's what you're going to do. Because that's what this is.
Honestly, it's the main reason I put the fry paradigm up.
Yeah.
I thought that was kind of not treated. It was such a foundational, rich basis of knowledge and a framework for thinking about the questions. I didn't see that foundation of knowledge carry through.
Yeah, I don't. It's funny talking with Hans Pertner, and I always ask him, why don't you just make reference to Fry? And I always found it so weird that he never referenced Fry.
Yes.
And he would talk about the kind of metabolic scope stuff that he was doing and integrating across tissues and things like that. And it sounded like bunk. I almost said something else. But we don't want to talk about the issue with gill size, because that's exactly what Tim has presented us.
Yeah.
Okay?
Yeah.
So I mean, because that's the difference in scaling of catabolism and anabolism. And so if we don't talk about that, then I could just say I totally agree with everything you said. I've never thought about this from a von Bertalanffy perspective. But the Fry paradigm is a wonderful paradigm that I teach all my students. And I don't understand why it was lost. And I think it was lost for maybe for one reason, that we stopped doing the kinds of experiments that you need to actually then use it on different types of fish other than brown trout, or and so that's it's sort of a call to arms to go back to the basics, to go back to the lab and understand how these factors interact to affect just the basic physiology of growth. And so anyway, I just wanted to say, kudos. I agree with everything you said, and I'm up for contributing however I can. I guess there's a number of people in the room who are interested in this. So.
Yeah, thanks, Mark. And maybe just get back to Terry's point. I mean, I actually think I'm thinking of a similar use as you are, is actually giving some predictions and forecasts, but trying to do that in a way that is both empirical, but is rooted in some of the foundational principles. And I think the von Bertalanffy is nice because it's such a simple model, even if it's oversimplified, but it has these linkages to these processes that we understand a bit.
Hi, Tim. I have two questions. The first was, could you just please repeat what you said the low-hanging fruit was? I think I zoned out for that, and I'm really curious.
Oh, the low-hanging fruit is this proposed easy step.
And can you say again what you mean by that?
Oh, so what I mean by that is, I think based on information that we already have, I think that something that could be done without an enormous investment of energy is to bundle the set of understanding about how these organismal core responses, so that would be anabolism and catabolism, how they respond to both oxygen and temperature, and filter that through or think of that through the filter of the von Bertalanffy parameter, to think then about predictions about how L infinity and K and ultimately growth rates are going to change in various environments.
Okay, cool, thank you. And so the second question that I have is, if I understand correctly, you say that K being related to catabolism we have clear expectations for how it should scale temperature. I assume you mean that's because we have quite a bit of understanding of how metabolic rates scale temperature. But then you mentioned that the anabolism term is, we know less about that, or the expectations are less clear. So I guess my question is, why should we expect them to scale differently with temperature?
That's a great question. So, and other people, feel free to chime in. I think the added difficulty with catabolism or anabolism is there's also a food availability piece. So the most energetically capable organism can't get food if there's no food to eat. And it's not clear how the changes in temperature affect food acquisition. That's a harder piece because it's being filtered through an ecological system.
Okay, and if food were not limiting, would they scale in the same way?
They're going to follow similar scaling laws, but the actual scaling parameters are going to be different.
Yeah, Tim, I was just, sorry, I'm going to keep talking because I do this stuff. So what about, I just would add the element of life stage. As you're talking about von Bertalanffy, and then you talk about differences in scaling factors and ultimately in environmental tolerance and in bottlenecks, I think the life stage component would be really interesting in this analysis as well. And we don't have as much data as we think we do about how environmental tolerance or things change across eggs, larvae, juveniles, and adults. Although there's been a lot of good theoretical work stating that juveniles have the
widest tolerance, perhaps. I mean, Pertner and Farrell in their paper, but
Mm.
I've only seen it in maybe a handful of species, maybe 3 or 4 species. So, and that would be another interesting facet to explore
Yeah.
as well.
So by changes in life stage, you mean like the threshold and tolerance would change by life stage, or would it, I mean, would it be different environment like the each life stage?
Yeah, I mean, so the scaling of growth is very different in larval. So larvae have a preference for protein growth. They have different types of organs. Their oxygen uptake is different. And they have isometric, they have very high costs of growth and high growth. And then there's a shift after the juvenile period. And you often see in species like cod, the highest water temperatures can be tolerated by juveniles. And it has everything to do with the scaling of, I don't want to say gill size again, but it does actually. Sorry. But so anyway, yeah, so different life stages have different environmental tolerance. And in cod, it shifts from like 16 degrees, which you would never believe a cod could grow in, 16, 17 degrees for juveniles, down to what you'd think like 6 to 8 degrees for larger fish. So, yeah.
Hmm.
So I have a question. So, is there, are there any like viable alternatives to variable Lansing curves? So like the, so like this idea of like a stage specific growth curves, might be, it seems like the only growth curves the only models I really hear about for fish growth are the variable Lansing curve. I want to just observe what curves.
Quick answer, there are lots, but the most
Yeah.
well-developed one is the biphasic, I think, which is
Yeah.
stage-specific, i.e. the point after maturation is the point that a different mollusk does.
Yeah. Also, I mean, this is just one way to integrate it, and you can always express it as, you can do a biphasic, if you really want to get crazy, you can make as many as you want. You can express this as, LT is a function of LT minus 1, and then you can make the von Bertalanffy parameters be stage specific.